everyone, I'm glad you're here, and welcome to the Chem Wizard podcast, your place for learning and listening to the magic of chemistry on the go. Grab a snack, maybe some coffee, and let us begin our adventure. In this first episode, I'm going to start by sharing my tips and tricks for studying for your first chem class, and study tips for the dreaded ACS if you have to take it. If you know, you know. Ugh, I know. Then we will move straight into the first lesson from Pearson's General Chemistry, Matter, Measurement, and Problem Solving. Alright, now for some tips and magic tricks for learning chem. So my first magic trick is practice, and did I mention practice? If you do not understand a concept, rewind, make a note of it, watch a video, read about it. I know that OpenStax, your textbook, are great reading resources. If you want to watch some videos, there are YouTube videos such as Organic Chemistry Tutor or Professor Dave Explains, stuff like that. And if you need further help, book office hours with your professor. Your professor loves to book office hours appointments, so take advantage of that. Make an actionable plan. Do not simply write, learn chapter 4. That won't get you anywhere. Write down your main goal and 2 to 3 actionable goals to reach it. So, for example, what I would do is write main goal, study chapter 4 for a test on Friday. Your actionable goals: spend 2 hours reading and watching videos about electron configuration. We'll get to that, don't worry. Work through 20 problems from problem set and test my knowledge with an online practice quiz. So 2 to 3 actionable goals that you can take. And do some online practice quizzes. Those really help a lot. Not to just passively learn the information, but actively engaging with it. And some other tips and tricks I have: you're not alone. If you can, make a study group, or if you have supplemental instructional groups, I know those really help me with my general chem class, attend those sessions. Book office hour appointments with your professor, ask a friend to quiz you. There's so many different things you can be doing. Use your resources to your advantage and find what works for you. Just because it works for your friend, it doesn't mean it will work for you. Test them out. One test will not make or break you. I repeat, one test will not make or break you or break your grade. So be easy on yourselves. Chemistry is not an easy course. Space out your learning and learn right away. Do not wait until there's 1 week until your test. Use spaced repetition. If you want to learn more about spaced repetition, I know Abdaal on YouTube does some really great videos about that. I'll link it in the description. Drink some espresso, coffee, Celsius, or green tea to get you a little bit of energized if you need that extra energy. And especially if you have an 8 a.m. chem class, I know those can be pretty grueling. Trust me, you might need it. Approach every lesson, hardship, success, failure as a learning opportunity and learning experience. Chemistry is not easy, but it is a beautiful and very interesting subject. General Chemistry 1 is the foundation for the rest of your chemistry courses, so it is key to build a good study routine and study habits right from the get-go. And lastly, have fun. Chem labs, extracurriculars, and experiments are very enjoyable, but you should have a grasp of the lecture lesson, so don't neglect those. Alright, let us begin the magic, what you guys are here for. So chapter 1, if you're studying from the Pearson textbook, is about matter, measurement, and problem solving. So it's really approaching chemistry right from the beginning. So let us begin. What do you think is the most important idea in all of science? Let's think about that. If we limit ourselves only to scientific answers, it would be this: the properties of matter are determined by the properties of molecules and atoms. The properties of water molecules determine how water behaves. The properties of sugar molecules determine how sugar behaves. Pretty straightforward. So the understanding of matter at the molecular level enables unprecedented control over matter. I would highlight this and put it on a cue card because this might show up on your multiple choice. All right, atoms and molecules. Atoms are the submicroscopic particles that constitute the fundamental building blocks of ordinary matter. Free atoms are rare in nature. Instead, they bind together in specific geometrical arrangements to form molecules. So, for example, the air contains carbon monoxide polytone. Carbon monoxide gas is composed of carbon monoxide molecules. Each molecule contains a carbon atom and an oxygen atom held together by a chemical bond, hence CO2. So small differences in atoms and molecules can result in large differences in the substances that they compose. Graphite and diamond are both made of carbon atoms, allotropes of carbon, this is another name for it. The atoms in graphite are arranged in sheets, so vertical sheets. By contrast, the carbon atoms in diamond are all bound together in a three-dimensional structure, hence why diamonds are so hard and rigid. Atoms and molecules continued. If we want to understand matter, it is essential to understand the constituent atoms and molecules. This is the central goal of chemistry. Chemistry is a science that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. I would highlight that and put it on a cue card. So how do we determine the properties of matter? We use the scientific method. You might have come across this in middle school. So the scientific method is empirical. It is based on observation and experiment. The scientific method is a process for understanding nature by observing nature and its behavior, and by conducting experiments to test our ideas. Key characteristics of the scientific method include observation, formulation of a hypothesis, experimentation, and formulation of laws and theories. So what are observations? Observations are also known as data. They are the descriptions about the characteristics or behavior of nature. So there was a scientist named Antoine Lavoisier, I really hope I'm pronouncing that right. He lived between 1743 to 1794. He noticed that the nature of constituents changed, but there wasn't any change in the total mass of material within the container during combustion. Observations often lead scientists to formulate a hypothesis or an educated guess. So a hypothesis is a tentative interpretation or explanation of the observations. For example, Lavoisier explained his observations on combustion by hypothesizing that when a substance burns, it combines with a component of air. A good hypothesis should be falsifiable. Hypotheses are tested using experiments, so what you'll probably be doing in your lab period. The results of an experiment may support a hypothesis or prove it wrong, in which case the scientist must modify or discard the hypothesis. Alright, the next part is scientific laws. It's a series of similar observations lead to the development of scientific laws. A brief statement that summarizes past observations and predicts future ones. Lavoisier summarized his observations in the law of conservation of mass. So, to quote, "In a chemical reaction, matter is neither created nor destroyed. It allows the prediction of future observations. The law can be tested using experiments, and it can describe the behavior of nature." Alright, a theory. It is one or more well-established hypotheses may form the basis for a scientific theory. A scientific theory is a model for the way nature is and tries to explain not merely what nature does, but why it does it. Theories are also tested using experiments. In your textbook, you might see a flowchart of the scientific method. I recommend studying. It will definitely help conceptualize the information a bit better. All right, the classification of matter. Matter is anything that occupies space and has mass. So, for example, textbooks, desks, chairs, animals, and humans, they're all composed of matter. Matter is classified according to A, its state, so its physical form, and B, its composition, the basic components that make it up. So classification of matter, its state. Matter can be classified as a solid, liquid, or gas based on the properties it exhibits. Phase changes. It's the state of matter changes from solid to liquid to gas with increasing temperature. So there's melting, there's freezing, all of these phase changes. Structure of atoms and molecules determines properties. Atoms or molecules have different orientations in solids, liquids, and gases, leading to different properties. So for example, in solid matter, it will be closer together. In liquid matter, there will be some space in between them. And in gaseous matter, the atoms are moving quickly next to each other. In solid matter, atoms or molecules pack close to each other in fixed locations. Although the atoms and molecules in a solid vibrate, they do not move around or past each other. Consequently, a solid has a fixed volume and a rigid shape. So for example, ice, aluminum, and diamond are all good examples of solids. Solid matter can be crystalline, in which case its atoms or molecules are in patterns with long-range repeating order. Table salt and diamond are good examples of solid matter. Others may be amorphous, in which case its atoms or molecules do not have any long-range order. So some examples include glass and plastic. All right, in liquid matter, atoms or molecules pack about as closely as they do in solid matter, but they are free to move relative to each other. Liquids have fixed volume, but not a fixed shape. Liquids' ability to flow makes them assume the shape of their container. So water, alcohol, and gasoline are all substances that are liquids at room temperature. In gaseous matter, atoms or molecules have a lot of space between them. They are free to move relative to one another. And these qualities make gases compressible. So if you have an image in your textbook, I recommend putting it on a cue card. It will help you visualize how gases can be compressed. All right, the next part of classifying matter is composition. Matter can also be classified according to its composition, a pure substance or a mixture. You might have a flowchart in your textbook. Again, definitely highlight it. The first division in the classification of matter is between a pure substance and a mixture. A pure substance is made up of only one component, and its composition is invariant. A mixture, by contrast, is a substance composed of two or more components in proportions that can vary from one sample to another. Pure substances categorize into two types, elements and compounds. This categorization depends on whether or not they can be broken down, or in other words, decomposed, into simpler substances. This refers to atoms. An element is a substance that cannot be chemically broken down into simpler substances. It's the basic building block of matter, and it's composed of single types of atoms, so for example, helium. A compound is a substance composed of two or more elements in fixed, definite proportions. Most elements are chemically reactive and combine with other elements to form compounds like water, sugar, etc. Mixtures, on the other hand, can be categorized into two types, a heterogeneous mixture or a homogeneous mixture. This categorization of mixtures depends on their uniformity of mixing. A heterogeneous mixture is one in which the composition varies from one region of the mixture to another. It can be made of multiple substances in different states, for example, a salt and sand mixture. Portions of a heterogeneous mixture have different composition and properties. A homogeneous mixture, on the other hand, is one made of multiple substances. All portions of a sample have the same composition and properties, like sweetened tea. Homogeneous mixtures have uniform compositions because the atoms or molecules that compose them mix uniformly. Separating mixtures. The components of mixtures are separable because the different components have different physical or chemical properties. Separation methods exploit these differences to achieve separation. For example, a mixture of sand and water, heterogeneous mixture, can be separated by decanting, which means, in simple terms, carefully pouring off the water into another container. You might have a lab on this. I'm not too sure about the curriculum. A heterogeneous mixture of an insoluble solid and a liquid can be separated by filtration. Filtration is a process in which the mixture is poured through filter paper in a funnel. A homogeneous mixture of liquids can usually be separated by distillation. Distillation is the mixture is heated to boil off the more volatile or easily vaporizable liquid. The volatile liquid is then recondensed in a condenser and collected in a separate flask. So, physical and chemical properties of matter. A physical property is a property that a substance displays without changing its composition. So this can be the smell of gasoline is a physical property. Odor, taste, color, appearance, melting point, boiling point, and density are all physical properties. Whereas a chemical property is a property that a substance displays only by changing its composition via a chemical change or chemical reaction. So the flammability of gasoline is a chemical property. Chemical properties include corrosiveness, acidity, and toxicity, among many others. So physical and chemical changes of matter. A physical change. Changes that alter only the state or appearance, but not its composition, so not what it's made up of. These are physical changes. The atoms or molecules that compose a substance do not change their identity during a physical change. For example, when water boils, it changes its state from a liquid to a gas. The gas remains composed of water, so in liquid form it was H2O. When it turns into a gas, it will be H2O. So the gas remains composed of water molecules, so this is a physical change. A chemical change, on the other hand, these are changes that alter the composition of matter. During a chemical change, atoms rearrange, transforming the original substances into different substances. So a good example of this is rusting of iron. This is a pretty popular chemical change. Iron combines with oxygen to form our iron oxide. So this would be a chemical change. And if you're curious, the reaction for this, it would be 4 moles, we'll get into the mole concept a bit later, of iron, plus 3 moles of O2 or oxygen gas. It will give us 2 molecules or 2 moles of ferrous oxide or iron oxide. So it would be 2Fe2O3. So you can see from 2 elements, it will form a compound. All right, moving on. A little bit of physics, so bear with me. If you're interested in physics, you might be a little more interested in this concept. If not, don't worry, we'll break it down. Energy, a fundamental part of physical and chemical change. Energy is the capacity to do work, and work is defined as the action of a force through a distance. So let's imagine you're a construction worker trying to move a box to the right. So the force that you're applying to the box, and once the box starts moving, it's doing work. force acts through a distance, work is done. But let's say a box is still going to be in its same place. No work has been done, because even though you're pushing the box and it feels like you're exerting a lot of energy, which you probably are, if the box doesn't move, you're not doing any work. When you push a box across the floor or pedal your bicycle across the street, you have done the work. Energy. Kinetic energy is the energy associated with the motion of an object. Thermal energy is the energy associated with the temperature of an object. Thermal energy is actually a type of kinetic energy because it arises from the motion of the individual atoms or molecules that make up an object. And potential energy is the energy associated with the position or composition of an object. So let's say there is something on the roof of a house. It will have the most potential energy at the top of the house. Once it starts falling down to the ground, that energy will be formed into kinetic energy. And then once the box hits the ground, it will have the lowest amount of potential energy because it's stable on the ground. But if it's contacting the ground, it will produce some heat. So that can also be some thermal energy. Energy is always conserved in a physical or chemical change. It is neither created nor destroyed. So this is coming back to our law of conservation of energy. Systems with high potential energy tend to change in a direction that lowers their potential energy, releasing energy into the surroundings. All right, a little bit of math here, so bear with me. Units of measurement. In chemistry, units, which are standard quantities used to specify measurements, are critical. The two most common unit systems are as follows: the metric system, used in most of the world, and the English system, which is used in the United States. So things like inches, feet, that would be the English system, and then meters, kilograms, that would be the metric. Scientists use the International System of Units, or the SI system, which is based on the metric system. The meter, or abbreviated as just a lowercase m, is slightly longer than a yard. 1 yard is 36 inches, and 1 meter is 39.37 inches. And if you have some cue cards, I recommend memorizing these units. Not only does it come in handy on the test if you're timed, but my professor did require us to memorize these. So if your professor doesn't, I'd go ahead and memorize them anyways, because the ACS, it'll definitely come in handy. Let's put it that way. The meter is defined as the distance light travels through a vacuum in 1/299,792,458 of a second, or we can just say 1/300 millionth of a second, and this is the speed of light. The kilogram. It's the mass of an object, is a measure of the quantity of matter within matter. The SI unit of mass equals 1 kilogram, and 1 kilogram equals 2 pounds, 3 ounces. A second common unit of mass is the gram. 1 gram is 1/1000 kilograms. Weight of an object is a measure of the gravitational pull on its matter. And a physical formula you might come across is W equals m times g, where g is the acceleration due to gravity, m is the mass, and w is weight. So I recommend really understanding the difference between weight and mass. And an analytical balance, something you'll see in your labs, measures the mass of something. The second, it is the measure of the duration of an event. An SI unit will be the second, or abbreviated as a lowercase s. 1 second, or 1s, is defined as the time it takes for a specific number of radiation events of a specific transition from cesium-133. So cesium is an element on the periodic table. The Kelvin, or uppercase K, is the SI unit of temperature. Temperature is a measure of the average amount of kinetic energy of the atoms or molecules that compose the matter. Temperature also determines the direction of thermal energy transfer, or what we commonly call heat. Thermal energy transfers from hot to cold objects. The Kelvin. Kelvin scale, or the absolute scale, assigns 0 kelvins, or absolute zero, to the coldest temperature possible. Absolute zero, converted into Celsius, would be negative 273 degrees Celsius, or negative 459 degrees Fahrenheit, is the temperature at which molecular motion virtually stops. Lower temperature do not exist. And 2 conversion formulas I would go ahead and memorize. So to convert into degrees Celsius equals degree Fahrenheit minus 32 in the numerator divided by 1.8. And to convert into Kelvin, it would be degrees Celsius, whatever you found, plus 273.15. All right, derived units. A derived unit is a combination of other units. Volume is a measure of space. It has units of length cubed, for example, centimeters cubed or liters, or capital L. Density is the ratio of a substance's mass to volume. It has units of mass over volume, or grams over milliliters. Density equals mass over volume. And an easy way to memorize this would be to draw a triangle, split it up into 3 parts, and on the top would be lowercase d, and on the 2 bottom parts would be m and v. And we can see that d equals m over v, and can manipulate the equation as well with some simple algebra. An intensive physical property, this is density. The physical property does not depend on the amount of substance. The physical properties of mass and volume that determine a substance's density are extensive. Extensive physical properties are dependent on the amount. Densities of substances are affected by temperature. So, we have an example for a density calculation. Mercury, or Hg on the periodic table, has a density of 13.6 grams per centimeter cubed. What is the mass in grams for 95 milliliters of mercury? And in pounds, they're also asking. We know that 1 milliliter equals 1 centimeter cubed, and 1 pound equals 454 grams. Again, I would put these on a cue card just for time's sake. So the strategy to find or to calculate this would be to, in the first step, convert milliliters to centimeters cubed, so we know that it's 1 to 1. Number 2, solve for mass in grams using the density relationship, D equals M over V. And number 3, convert grams to pounds. So we know that D equals M over V. If we bring M over, we know that's D times V. So we'll take 13.6 gram per centimeter cube multiplied by 95 milliliters. We know that 95 milliliters equals 95 centimeters cubed, so we can already take away milliliters and replace that with centimeter cube. So 13.6 gram per centimeter cube multiplied by 95 centimeter cube, we know that we can cross out centimeter cube from the numerator and denominator. So we're left with 1.3 times 10 to the 3 grams when we multiply it through. And then in the second step, we know that 1 pound equals 454 grams. So we'll take 1.3 times 10 to the 3 grams. Make sure you're also putting it in brackets. That helps with bed mass or order of operation. We multiply by, on the second bracket, 1 pound over 454 grams. Grams cancel out. It's pretty satisfying. And we're left with 2.8 pounds. Next part is prefix multipliers. This is the International System of Units, uses the prefix multipliers. These multipliers change the value of the unit by the powers of 10, just like an exponent does in scientific notation. For example, the kilometer has the prefix kilo, meaning 1,000 or 10 to the 3 meters. Teragram equals 10 to the 12 grams. Microgram equals 10 to the negative 6 grams. I would go ahead and memorize these prefix multipliers just to make things a little bit easier on your test. Counting significant figures. Scientific measurements are reported so that every digit is certain except the last, which is estimated. So for example, 5.213, the 3 is estimated, but 5.21 will be certain. Significant figures deal with writing numbers to reflect precision of the measurement. The precision of a measurement depends on the instrument used to make the measurement. The preservation of this precision during calculations can be accomplished by using significant figures. The greater the number of significant figures, the greater the certainty of the measurement. To determine the number of significant figures in a number, follow these rules. So, number 1, all non-zero digits are significant. Some examples can be 28.03. Everything but the 0 will be significant. Or another example, 0.0540. 54 are significant, but the zeros aren't. Number 2, interior zeros. Zeros between two non-zero digits are significant. So for example, 408, the 0 in between will be significant. Or 7.0301. Those two zeros are significant. Number 3, leading zeros. So the zeros to the left of the first non-zero digit are not significant. They only serve to locate the decimal point. So for example, 0.0032, those zeros are not significant. Or 0.00006, those zeros are also not significant. Number 4, trailing zeros, so the zeros at the end of a number, are categorized as follows. Trailing zeros after a decimal point are always significant. So for example, 45.0000, those are going to be significant. 3.5600, those zeros are significant. Trailing zeros before a decimal point and after a non-zero number are always significant. So 140.00, 140, the 0 before the decimal will be significant. Or 2500.55, the zeros before the decimal point are significant. Trailing zeros before an implied decimal point are ambiguous and should be avoided by using scientific notation. So for example, if you see 1200, that number is ambiguous. You can't really determine the number of significant digits. But if we convert that into sig figs, 1.2 times 10 to the 3, 1.2 will be 2 significant figures. 1.20 will be times 10 to the 3 will be 3 significant figures. And 1.200 times 10 to the 3 will be 4 sig figs. Decimal points are placed after one or more trailing zeros if the zeros are to be considered significant. So we can have something like 1200 and then a decimal point. This will be 4 significant figures. All right, the next part is exact numbers. Exact numbers have an unlimited number of significant figures. Exact counting of discrete objects, for example, 12 apples. Integral numbers that are part of an equation, so for example, y equals 2x plus c. And defined quantities, conversion factors, or as an example, 1 milliliter equals 1 centimeter cubed. Significant figures in calculations. In calculations using measured quantities, the results of the calculation must reflect the precision of the measured quantities. We should not lose or gain precision during mathematical operations. Rules for calculations involving significant figures. Multiplication and division rule. In multiplication or division, the result carries the same number of significant figures as the factor with the fewest significant figures. So, for example, Let's say we have 1.052, that's going to be 4 sig figs, times 12.504, that's 5 sig figs, multiplied by 0.53, we know this is going to be 2 sig figs, the leading zero is not significant. How many sig figs do we think they have? So we get a result of 6.7208. We'll always take the lowest amount or the fewest amount of significant figures. So the final answer should be recorded as 6.7 because we know the lowest amount of sig figs was 2 sig figs. So we really only need 6.7. How about division? Let's say we have 2.0035, this is 5 sig figs, divided by 3.20, this is going to be 3 sig figs. We get a result of 0.626094. It's a lot of numbers, right? We can condense that into 3 sig figs because we know that 3 sig figs, it's the fewest amount of significant digits. So it'll be 0.626. I definitely recommend doing some examples in, let's say, your Pearson Chem problems or your textbook, anything just to practice these through on paper. So the next part is rules for calculations for addition and subtraction rule. In addition or subtraction, the result carries the same number of decimal places as the quantity with the fewest decimal places. So what I recommend to do for this is, let's say we have 2.345 and 0.07 and 2.9975. The result will be 5.4125. I recommend lining these numbers underneath one another, like the decimal points are all lined up underneath each other, and all the decimal places are lined up underneath each other. And wherever you draw the vertical line, so let's say we have 2.345, 5 will be left on the right, 0.07, that all makes it onto the left, and then something like 2.9975, the line will cut off between 2.99 and then the 75. So our result, when we extend that vertical line, it won't be 5.4125, it'll be 5.41 because that's where our vertical line cut it off. Or let's say we have 5.9 subtracting 0.221. Same deal. We draw the vertical line, we line up all the decimal places, and we get a result of 5.679. But we see that the vertical line cuts off between 5.6 and then the 7.9. We get a final result of 5.7 because the 7 rounds the 6. Which comes into the next topic, rules for rounding. When rounding to the correct number of significant figures, round down if the last digit dropped is 4 or less, and round up if the last digit dropped is 5 or more. So round to 2 significant figures. 5.37, the 7 rounds 3 up, so that rounds to 5.4. 5.34 rounds to 5.3, 4 doesn't round 3 up. 5.35 rounds to 5.4, and 5.349 rounds to 5.3. And notice in the last example that only the last digit being dropped determines in which direction to round. Ignore all digits to the right of it. Rounding in multi-step calculations. To avoid rounding errors in multi-step calculations, round only the final answer. Do not round intermediate steps. If you write down intermediate answers, keep track of significant figures by underlining the least significant digit. So for example, 6.78 times 5.903 times, in brackets, 5.489 minus 5.01. So let's calculate what's in the brackets first. So before that, let's write out what we first had, 6.78 multiplied by 5.903, multiplied by what we received in the brackets, we got 0.479. We're going to underline the least significant digit, which is 7, in the 0.479, and we get 19.1707, or a final result of 19. The next part in our first chapter is precision and accuracy. It's a pretty important concept to learn, especially during your labs. Significant figures indicate the precision of a measurement. Precision refers to the reproducibility to the measurement, so how can we reproduce them? And accuracy. This refers to how close the measured value is to the actual value. So let's consider the results of 3 students who repeatedly weighed a lead block known to have a true mass of 10.00 grams, indicated by the solid horizontal blue line on the graphs in your textbook, if you're following along with that. So let's see. In trial 1, student A got 10.49 grams, student B got 9.78 grams, student C got 10.03 grams. Trial 2, student A got 9.79 grams, student B got 9.82 grams, student C got 9.99 grams. And we have a few more trials. We then calculate the averages. So student A got an average of 10.13 grams, student B got an average of 9.79 grams, and student C got an average of 10.01 grams. If you're following along with your textbook, you see that student A, when graphed, we see that the blue line indicates its true mass and the red line is the average. So the results are inaccurate and also imprecise. In student B, we see that it is inaccurate, but it is precise because it levels up more or less. And in student C, it is both accurate and precise, according to the results. So measurements are said to be precise if they are consistent with one another, so how close they are, and accurate only if they're close to the actual value. The results of student A are both inaccurate, so not close to the true value, and imprecise, they're not consistent with one another. This is known as random error. And random error is an error that has the equal probability of being too high or too low. The results of student B are precise, so they are close to one another in value, but they are inaccurate. And we call this a systematic error. It's an error that tends toward being either too high or too low. And the results of student C display little systematic error or random error. They're both accurate and precise, and this is pretty much optimal. Solving chemical problems. Most chemistry problems you will solve in this course or General Chemistry 1 and moving forward are unit conversion problems. Using units as a guide to solving problems is called dimensional analysis. You might have heard your professor throw that word around. That's all that it means. And units should always be included in calculations. They are multiplied, divided, and canceled like any other algebraic quantity that you might see in your math class. Dimensional analysis continued. A unit equation is a statement of two equivalent quantities, such as, and I'd memorize this for your test, 2.54 centimeters equals 1 inch. A conversion factor is a fractional quantity of a unit equation with the units we are converting from on the bottom and the units we're converting to on the top. So for example, 2.54 centimeters over or a slash 1 inch is the conversion factor to convert inches to centimeters. Most unit conversion problems take the following form. Information given multiplied by our conversion factor or factors equals the information we were trying to find or information sought. So given unit times desired unit over the given unit to cancel top and bottom equals the desired unit. So a good example, convert 2 inches to centimeters. We'll take 2 inches multiplied by 2.54 centimeters, our desired unit, over 1 inch, and we cancel out inches and inches from top and bottom. to get 5.08 centimeters. Dimensional analysis, I promise is the last one. Units raised to a power. When building conversion factors for units raised to a power, remember to raise both the number and the unit to the power. I cannot tell you how important this is and how it will pretty much make or break your answer on the test. For example, to convert from inches squared to centimeters squared, we construct the conversion factor as follows. I promise you, if you write it down on your test on a scrap piece of paper, it will help a lot. So 2.54 centimeters equals 1 inch. We know this. Take everything, so 2.54 centimeters, take that in brackets, square it, equals 1 inch, all in brackets, square that. Then, with distributive properties, you might have learned that in your algebra class, we get 2.54 squared centimeters squared equals 1 squared inch squared. Calculate 2.54 squared. So we get 6.45 centimeters squared equals 1 inch squared. So anything 1 to the power of something will be 1. 6.45 centimeters squared over 1 inch squared equals 1. And that's actually all I have for you today in the first lesson. I really hope that helps. Listen to this as many times as you need to grasp on these concepts. It will build off, the course will build off of these concepts, so make sure you do have a good grasp on it, because all your math problems inside and outside of chem class will be using these concepts, dimensional analysis, derived units. So I really do recommend writing it on a cue card, quizzing yourself, maybe finding some Quizlets. And with that, thank you so much for listening to the first episode of the Chem Wizard. I really hope you learned a little bit of magic today. And with that, I hope you have a magical day. Take care.